we're getting right up on 11:10. Welcome everyone to this week's CDAR Risk Seminar. I'm delighted to have CDAR co-director Bob Anderson, who's going to present today on work with a geographically very broad group of co-authors. Bob, of course, is in Berkeley. Kevin Duanmu was in Berkeley as Bob's postdoc and is now at Harbin University, that's in China, I think rather near Mongolia. Ali Khan, who is at Johns Hopkins, and Metin Uanik, who is at Queensland University in Australia. So everyone cares about this topic, obviously, climate change, general equilibrium and climate change. And Bob, I'll put myself on mute and turn over to you.
Thank you. So this is going to be a fairly broad overview of a big project, and I also want to put it into context in terms of how the general equilibrium theory developed and why it developed the way it is. So general equilibrium theory really goes back almost 250 years to Adam Smith's The Wealth of Nations, a book published in 1776, and continued very actively until the 1970s and 1980s. And then as things were basically worked out, people started looking at other areas. And I think that historical period is important because most of this time was characterized by scarcity. So even in developed countries, more is better is a natural assumption. And this monotonicity assumption that people are better off if they have more consumption is something that really pervades the theory. In terms of related policy, although industrial air and water pollution became an issue in the 20th century, perhaps early in the 20th century, substantial regulation did not really ramp up until the 1970s. Ironically, perhaps under the Nixon administration, and the US ramp up happened under the Nixon administration. So the theory almost always has this assumption that more is better embedded into it. And of course, it also recognized that there were pollution and externalities. So externalities is an economic term for something I do has an impact, either beneficial or more typically adverse on you. So it tended to, not really address directly the issue of some things being actually bad, but rather regarded pollution as being something that's generated in the course of making me better off, but then has adverse effects on you. But nonetheless, my consumption is a good thing for me, and we treat pollution as being kind of a spin-off that has some other effects. So it nonetheless does try to address pollution, and it typically does that through so-called Pigouvian taxes. So Pigou was a British economist in the early 20th century. So basically a Pigouvian tax is designed to either encourage things that have positive externalities or discourage things that have negative externalities. So a tax on smoking is, tax on cigarettes is a typical example of a Pigouvian tax. If it's a pure Pigouvian tax, it's really focused on reducing the impact of secondhand smoke. It's reducing the externality on me, but it also directly discourages consumption of tobacco. But the equilibrium theory, general equilibrium theory, doesn't really deal with the determination of the appropriate levels of taxes. And the determination of those taxes is not really built into the determination of equilibrium. So it's really very difficult in general equilibrium to say that the level of tax is appropriate. Economic theorists have certainly studied the relationship between, let's say, carbon taxes as a way of controlling global warming or cap and trade. And these are in some limited sense equivalent to each other, but one needs to understand the sense in which they're equivalent and the sense in which they're not. But in any case, these were studied primarily in partial equilibrium. So instead of looking at all markets simultaneously, you look only at a particular market, like the market for generating electricity, and within that context, look at the effect of a carbon tax or cap and trade. And it doesn't allow the consideration of economy-wide spillovers. Now, there's another approach to externalities, which is based on the Coase theorem. So this is Ronald Coase of the University of Chicago. This was, I guess, in the 50s, roughly. Anyway, the Coase theorem is a true theorem, but its actual applicability is open to discussion. So basically, it says if you establish property rights and then allow bargaining, then you'll get a good outcome in an economy. So, for example, we could either say that everybody has the right to burn coal and generate carbon dioxide, and then the people who are adversely affected that will enter into a bargain to pay people not to burn as much coal or to substitute a different technology. Or on the other hand, everybody could have the right to avoid global warming, so no new CO2 emissions, and then the people who want to emit CO2 would bargain with those who have the right to be free of it. And I mean, the theorem is true. It says that the outcome of that bargaining, where the bargaining occurs in a particular way, is always Pareto optimal. It gives you an outcome that you can't make everyone better without making somebody worse, but the practicality of the bargaining is quite dubious. So, we've got a problem if we want to apply GE, which is one of the main benchmarks of microeconomic theory, that it's not really set up for dealing with global warming.
Bob, can I ask a question that I've always wondered about? I'm obviously just an amateur here, but in my reading of the Coase theorem, Coase was quite critical of Pigou. And
so I was not aware of that, but I guess he would have said that Pigou was irrelevant because bargaining would take care of itself, so that there's no role for government to set taxes to work these things out. Is that roughly what he said?
No, he says that it's, I don't have the quote in front of me, but I'll get it for you later. More or less, it's hard to understand why a theory as faulty as Pigou's could be so influential. Perhaps the reason is that it wasn't clear. I mean, he was a scathing remark, which I have highlighted in my paper, and I just, you know, it obviously caught my attention, and would love to get your thoughts on it at some point.
Okay, well, I need to read what he says, but my guess is that that Pigou doesn't fit neatly in general equilibrium, and which he doesn't. I mean, it doesn't really fit there. It's really a model for partial equilibrium, and if, you know, Coase might well have criticized that with justification. Anyway,
okay, thank you.
Let's proceed. So the basic equilibrium notion in general equilibrium is typically referred to as either Walrasian equilibrium, or sometimes using the more modern formulation Erediver equilibrium. But this comes from a book by Walras, who is a French mathematician, 1874. And in it, the basic idea is that firms take, firms and consumers take a price vector P as given. So this is a vector which specifies the price in dollars or euros or whatever currency of all of the commodities. And then once they take that, what taking it as given means they either don't believe they can influence it or act as if they can't influence it. And then consumers maximize utility over their budget sets, where the budget set is what they can afford to buy given the price factor P, and firms maximize profit over their production possibility sets. Now, consumers taking the prices as given is a very reasonable assumption. However, firms maximizing profit taking prices as given is a dubious assumption because much of the economic activity in a modern industrial economy is carried out by large firms that do in fact have pricing power. But the formulation of this notion of equilibrium assumes that either they don't have that power or they act as if they don't. And it has a fictitious Walrasian auctioneer who chooses a price factor P, so that supply equals demand. As I said, the modern formulation is the Erediver equilibrium, which I'll describe in more detail later on. Now, I mean, I think the key bullet on this slide is that P is set so that supply equals demand. And I think that that is probably pretty accurate as a description of a modern industrial economy. There certainly are regulations that affect it, although you can view those things as affecting the supply or affecting the demand for goods. And profit maximization taking the price P is given is of is of doubtful economic substance given the presence of large firms. But nonetheless, we do see that there is a price factor P. People use that price factor in order to guide their trading. Consumers certainly do. And supply and demand are roughly equated in the goods market. So while the particular notion here of taking prices given may be of dubious economic relevance on the production side, equating supply and demand is something that seems to be very solid empirically. And we want to look at how, given that supply and demand are equated, how we can manage a big externality like global warming. So I've already talked about a strong assumption that price taking on the part of firms is a not very reasonable assumption in general equilibrium. And there are a number of others which are in the appendix to these slides, but I don't want to really talk about them. Why we use GE is, first of all, it's the benchmark economic model for perfect competition. So any example of antitrust, for example, cares a lot about the fact that firms don't take prices as given, but it looks at comparing a particular outcome in which firms do have some monopoly power to the benchmark of perfect competition. So that's one reason. Second is that Erediver equilibrium has appealing welfare properties. Equilibria are Pareto optimal, for example, and one can, by redistributing endowments, achieve any Pareto optimum that you like through a market mechanism. One thing I want to focus on here is that computable GE models, so these are obviously, they're models of a whole economy, and they are somewhat stylized, but they're a lot more specific than the abstract general equilibrium theory. So they would have different industries, and they would have consumers with certain kinds of tastes, and they can be used to determine the effect of policy changes that could be widespread. So what do I mean by a widespread spillover effect? Well, if we impose a carbon tax in the US, that increases the cost of smelting aluminum in the US. The production of aluminum from aluminum ore is extremely energy intensive, uses lots of electricity. Okay, if you increase the cost of smelting, you're going to cause layoffs of metal workers in the US. So maybe aluminum will be imported from other countries rather than produced in the US. It also will cause layoffs of brewery workers in the US because much of beer is sold in aluminum cans, and also bauxite miners in Jamaica. So bauxite is one of the main ores from which aluminum is produced, and the US imports it. The biggest source of imports of bauxite from the US is Jamaica. So a carbon tax affects a lot of people, and you can't really analyze that in partial equilibrium, but you can analyze it in an abstract GE model, and a computable GE model will let you estimate the effects and look at whether people should be compensated. There are going to be winners and losers, and try to see whether a given loser deserves to be compensated. So maybe the oil companies don't deserve to be compensated, but other people who are impacted by a carbon tax you may want to compensate them, both as a political device in getting the policy approved, but also because people who, for example, are working in industries that ramp down and need to move to different jobs and need retraining and so forth, they arguably deserve some compensation. And partial equilibrium models in which it's easy to talk about Pigouvian taxes don't permit this kind of spillover analysis. So what's our goal in this project? It's to accept the well-documented flaws in GE, because doing so allows us to do analysis of spillover effects. It's to identify and resolve less documented flaws that are specific to climate change. So we've looked at papers in the literature that purport to be relevant to climate change, and we find that there are assumptions in them that really don't make sense in this study. So we want to identify what's been inappropriately assumed that's specific to climate change and resolve that to the extent possible, and then show that the model we get is coherent, by which we mean we can prove there is an equilibrium. And that also tells us that the computable GE models can find the equilibrium in a computationally relatively efficient way. Okay, so let me talk about the problematic aspects. So first thing is that it is typically assumed in order to show existence of equilibrium in production models that firms have free disposal in production. Okay, so this is a huge problem, and we'll see why in this slide, and I'll have a theorem that shows how serious it is in a little while. So let's first of all start in the context of exchange economies. So here the production has already happened, and people are simply trading in order to divide up the goods that were produced. More is better is typically assumed, as I noted at the beginning, but more atmospheric CO2 or particulate pollution is definitely not better. So the monotonicity assumption is problematic. And in production economies, free disposal in production is typically assumed. So what does this mean? So suppose that Y is a feasible production vector. So it will have some negative components that represent inputs and positive components that represent outputs of production. And Y being feasible means it's possible for a firm to take the input specified by the negative components and produce the output specified by the positive components. And the assumption that's typically made is if Y is a feasible production vector and Z is less than Y, so Z is less than or equal to Y in all components and strictly less than at least one, then Z is also feasible. So let's look at what that says in the market for generating electricity. So let's suppose the commodities are coal, electricity, and carbon dioxide. Okay, well, if I use appropriate units, then -1, 1, and 1 is a feasible production vector. So what does that mean? It means I can use 1 unit of coal as an input, I burn it, and I produce 1 unit of electricity and also 1 unit of carbon dioxide. Okay, so that's roughly the technology of producing electricity by burning coal. Well, under free disposal in production, if -1, 1, 1 is feasible, so is -1, 1, 0, because -1, 1, 0 is less than -1, 1, 1. So it says you can burn 1 unit of coal to produce 1 unit of electricity and 0 carbon dioxide. Well, of course, that's not physically possible. The unit of carbon dioxide has to go somewhere. Either it goes into the atmosphere or it's converted back into carbon and oxygen, although that takes a lot of energy to do, or it's sequestered, but something has to happen to it. It's not feasible to burn coal and not produce carbon dioxide. Okay, maybe you recapture it, but if so, that's got to be included explicitly in the modeling and accounting of the economy. So I'm going to use the word accounting on a number of cases. If you're going to impose a tax on something, you have to be able to account for it. And free disposal in production, what it's saying is it allows you to drop the carbon dioxide emission from the accounting, which means that, at least in the model, you can't tax it. So this assumption is something we absolutely can't live with. Okay, problematic aspect number 2, many papers assume a fixed technology for generation and transmission. Well, this is in the papers that want the price, well, they want preferences to be monotonic for the consumption goods. So I can get that if I treat electricity consumption as the good. And it's obviously a value to me. I'm willing to pay for it, so it has a positive price. And consuming more gives me higher utility. And of course, it creates a negative externality, but these papers try to net out, well, they try to address the negative externality, but in a sense net it out so that the preferences are still monotonic for electricity, and the price of electricity is positive. My preferences are monotonic in my own electricity consumption, and we'll try to shove the next negative externalities aside while keeping the monotonicity assumption. Well, what's wrong with this? Well, it tacitly assumes that each unit of electricity consumed yields exactly 1 unit of CO2 emissions. Okay, if I'm going to sweep the CO2 kind of under the table and treat electricity consumption as the commodity that I'm going to perhaps tax in order to control CO2 emissions, well, it doesn't really get at what I want, because different technologies are either much greener or much less green. So burning coal is about the worst. It's worse than burning natural gas. Nuclear doesn't produce any CO2 emissions, although it has other byproducts that are highly toxic. Solar, wind, hydroelectric, and geothermal are much more benign, but not also without some negative externalities. So Donald Trump would like you to focus on the fact that windmills sometimes kill birds. We don't want to focus on that, but we don't want to ignore it either. That should be in the accounting. But one should also be able to, let's say, compare burning coal to generating electricity by windmills and make a sensible choice between them. So a model that kind of treats the global warming as an essential and necessary component of my use of electricity doesn't let me get at giving incentives to improve the way it's generated. Okay. One of the good things is that these technologies, many solar, wind, hydroelectric, geothermal, yield zero CO2 emissions at the margin, but they do have some fixed emissions for building the plant. So these plants will typically involve, let's say production of steel or concrete, both of which emit CO2. So that fixed emission needs to be accounted for. Another big thing with electricity is that demand is time varying, but generation is not readily adjusted. It takes time to ramp up or ramp down generation. And so the emissions from one unit of electricity may be very different at different times. Battery technology is getting cheaper, but is still relatively expensive. This could be resolved if we had perfect storage technology. Transmission losses, so where the electricity is generated affects the emissions, because I have to generate more if I generate it far away from where it's used. So this is a complicated market, and I can't really reduce the thing that contributes to global warming, the CO2 emissions, simply to being a fixed function of my energy use. Third problematic aspect is the way ownership is treated in the Erediver model. So what it really does is it assigns ownership of commodities, and with a mindset that more is better and prices of commodities are all positive, it just kind of assumed that people will actually gobble up and use up whatever they're able to buy. So I think that was the focus. But the literature didn't really think hard about what this meant. And in fact, it doesn't force you to use up the commodity. It conveys ownership. And ownership involves the right to consume the commodity, but doesn't entail the obligation to dispose of it. We need to have a tweak of the model that says if you buy up, well, if you're paid to absorb CO2, you actually really have to get rid of it. And that's not something that's a feature of the Erediver economy as it's been conceived. And finally, the example is mostly due to Hara, who I'll mention again as we go through this, that equilibrium often vests ownership of bad. So these are things like pollution in an either numerically small and or a low income group. So if you take a model with a finite number of agents and look who ends up absorbing the pollution, well, you are discouraging pollution by putting a negative price on it. And then what happens in equilibrium in the model is people who have relatively low income say, yeah, sure, I will gladly absorb this pollution or live near it or be adversely affected by it in return for a cash payment, which I can then use to increase my consumption of goods that I want. And in fact, in examples, this turns out to be so extreme that it raises questions about whether it's even physically possible. That is, you can get in models either a very small group or even a single person ends up absorbing all the CO2. And of course, they don't have the capacity to do that. So there's something wrong in the connection between the model and what people are actually able to do when we're talking about pollution as the good that they accept in order to supplement their other consumption. Okay, so those are the three things that I think that we've identified are problems with the formulation of general equilibrium, specifically for the consideration of global warming. I want to talk also about externalities. We want to have externalities in our model, and we will, but we need to look at what kinds of externalities we need. So some are widespread. where my welfare is affected by decisions of other agents everywhere. So CO2 emissions basically impact globally. The consequences may be different in different regions, but if I release CO2, it basically disperses through the atmosphere, and CO2 locally is not toxic. If I have a very high buildup of CO2 in a closed building without sufficient ventilation, it might be an issue, but locally CO2 is not toxic. On the other hand, some things are very toxic locally. So particulates are an example of things that make breathing quite difficult. And on the other hand, particulates tend to wash out of the atmosphere. So these are local phenomena. Toxic waste disposal, if it can be contained locally, is also a local phenomenon. And externalities can also be persistent or transient. So once CO2 is emitted, it stays up in the atmosphere for centuries, very slowly removed by other processes, and toxic waste may last for thousands of years. Nuclear waste lasts for tens of thousands of years. On the other hand, externalities may be transient, so particulates fortunately go away with time, they get washed out. So here's the Erediver model, and we're going to modify it to allow externalities and negative prices. So we've got capital K commodities. So these are the goods that people consume, but they could also be goods that are inputs to production. And one of the commodities is labor. So I supply my labor as an input to the production process. So a firm pays me a wage. In doing that, it's buying my labor, and that's an input to the production process. And then once I've sold it, I can't use it for my leisure. So I've got capital J firms, and their production sets that represents the set of vectors that they can take with the negative components as inputs and produce the positive components as outputs. I've got capital I agents, and they're endowed with a non-negative consumption, a non-negative endowment factor. So in most cases, the biggest element of this is their own labor. So they will supply their endowment of labor or a portion of it to an employer in the production process. And they also own shares in the firm, so that each individual has a non-negative share of each firm. And the total shares outstanding in every firm add up to 1. Okay, we've got a price factor P, and it's not 0, but it may have individual components that are 0 or negative. So for the bad things, the price is going to be negative, and people can get paid in order to absorb the pollution. Pollution will have a negative price. Okay, then we get a production vector, and our model actually is more general than this. So people have observed that you can prove existence of equilibrium and general equilibrium without assuming that firms maximize profit. But to simplify, we will assume here that firms maximize profit, which just means they maximize the dot product of the price vector times the consumption vector, the production vector Y over their set of production possibilities. An allocation is an assignment of consumption of the K goods to all of the agents I, and demand for an agent maximize agent I's preference given the price P, and relying externalities, so your preference can depend on the consumption of every other agent. So agent I's preference depends on consumption of everybody else. It doesn't depend on his own consumption, because that's well, actually, let me be careful here. Agent I's preference tells you which of his own consumption bundles he likes better and which ones he likes worse. And that doesn't go away, but his preference over his own consumption depends on the consumption of everyone else. That's what this is saying. And also depends on the production choices. Why? So if the factory next door is emitting a lot of particulates, then that affects Agent I's preference. Maybe he values an air cleaner more. And subject to the budget constraint that the total value at the price P of what Agent I consumes is less than or equal to the value of Agent I's endowment, plus Agent I's share of the profits of all of the firms. Okay, so there are two notions of equilibrium, and the difference is quite important for studying climate change. The first is non-free disposal equilibrium, which says that supply equals demand. Demand is on the left side. This is the sum of the demands of all of the agents is exactly equal to the sum of the endowments plus the sum of the production vectors. And moreover, this X specifies an allocation. It's that every agent I is in his or her demand set given the price P and the consumptions of the other agents and the productions of the firms. And on the other hand, free disposal equilibrium is exactly the same, except it replaces this equality with a less than or equal sign. So it says that demand is less than or equal to the supply. There's some stuff left over. And that stuff that's left over is freely disposed. What's left over is the difference between the right side and the left side. And even if the price of a disposed good is negative, no one's responsible for paying for the disposal in a free disposal equilibrium. Okay, it just drops out of the accounting. I can't charge anyone for it. Whereas in free disposal equilibrium, first of all, I can charge people if they emit something. And second, the equality here requires that everything is that's released is actually used. So if the CO2 is produced, that's fine. That's not prohibited, but it's then got to be either it's either dispersed into the atmosphere in a way we account for, we don't just ignore it. So that's number one, or it's sequestered or something else is done to eliminate it. But the equality sign in non-free disposal equilibrium means that we account for that CO2 that's produced. So I explained in an example before why the assumption of free disposal in production is a bad one. And this is actually a theorem that shows just how bad it is. So if any firm, one firm doesn't need all of them, has free disposal in production, then under a mild assumption on consumer preferences, which is called local non-satiation, I don't need to detail what it is, but it's a lot weaker than monotonicity. Then every free disposal equilibrium can be disguised as a non-free disposal equilibrium. So I can take any equilibrium that dumps whatever amount of pollution you like into the atmosphere or into the water, and I can pretend that it's a non-free disposal equilibrium. So this is clearly something I cannot allow. I need to avoid the assumption of free disposal in production. The proof's quite simple, but I'm also running more slowly than I'd expected. So let me skip it, and people in the slide can easily afterwards read the slides and understand this is really an elementary fact. So we really can't allow free disposal in production as an assumption. On the other hand, we don't necessarily want to prohibit all free disposal. So, we're going to choose to allow some free disposal and control others. So the atmosphere is mostly nitrogen, 78%. It's about 21% oxygen, and it's actually only 0.04% CO2, which has roughly doubled in the last 250 years. So this is having a big effect on climate, but it's astonishing that it has such a big effect on climate, given how small the amount of it is. But the main point I want to make is that atmospheric oxygen is a good. I mean, it's essential. We would all die if we didn't have any of it. But the supply exceeds the demand, and there's no conceivable technology we can use that would really reduce this. So, all of the burning of fossil fuels that's happened has doubled the CO2 in the atmosphere, but that's made a really negligible difference in the amount of oxygen in the atmosphere. There's no way we can use it all. Demand is less than supply. The price of atmospheric oxygen is zero, and this is as it should be. Okay, at equilibrium, that's what we want to have. Okay, CFCs and HCFCs, these are chemicals that were used in propellants in aerosol cans. They're bad because they deplete ozone in the upper atmosphere, and ozone helps to shield the Earth from harmful emissions from harmful radiation from the sun. They've been phased out under the Montreal Protocol, which is from I think 1976. And that's a regulatory solution, which in our setting would be equivalent to setting the price to be minus infinity. You set the price so high that nobody produces any of them. And on the other hand, CO2 is bad. It contributes to global warming. It continues to be freely disposed. So, if I drive my car, I'm not directly anyway paying a charge for the CO2 that my car generates. But it's socially desirable to reduce or eliminate the amount of disposal by imposing a negative price. So our desired model is a general equilibrium model in which all commodity disposal is explicit. So, we can say we're not going to use up all the oxygen. We're going to leave it in the atmosphere. We're going to dispose of it. On the other hand, CO2 emissions, we want to account for them explicitly, and we don't want to hide it. And we want to be able to price it. So we want to be able to either do a cap and trade or impose a tax on CO2 emissions. And we want some goods to be fully consumed, supply equals demand for those goods, and have a positive price. Some goods exhibit satiation, so there's a zero price and they're freely disposed. Some bads are tolerated, okay? Some will just choose to tolerate. We've done that with CO2 emissions for a long time. We can no longer do that, but some will choose to tolerate. Some bads will be regulated by a negative price, and some are eliminated, like CFCs, by a large negative price. And it's a choice variable which commodities are disposed and in what quantities. And preferences of agents reflect the global and local dichotomy and transient long-lived nature of externalities. So with finitely many agents, there is a theorem that comes close to doing this. So this is a paper from 40 years ago by Russian mathematician Makarov in the Journal of Mathematical Economics, and it allows quite general global externalities. It allows also local externalities, although it doesn't actually model them via geographical structure. So one of the things one would like to have, and we don't currently, is a geographical model in which nearby pollution of certain kinds affects you, but far away ones doesn't. And it doesn't assume predisposal in production. It assumes the production set Y is compact and convex. And people argue about whether compactness is a problem or not. There are arguments that it isn't, that say because the amount of inputs that are available are finite, even if in theory the production set is not compact, the things that you can actually produce given the available inputs is a compact set. Convexity is more of a problem, and this is a general issue in general equilibrium. It's related to the fact that you get large firms. The failure of convexity of production sets is essentially the reason why you get very large firms that have market power. Okay, but it seems better than what's typically assumed in GE, which is the production set's a convex cone. So there's something about the cone structure that is really inconsistent with the presence of large firms, and by allowing compact convex production sets, we get a model that's consistent with existence of large firms. But unfortunately, in the finite model, as I mentioned briefly earlier, equilibrium typically assigns ownership of BADs to a numerically small group of lower income consumers, and it is not clear that they actually have the means to dispose of it. So how are we going to resolve these problems? So I've got two resolutions on this paper. The first is the correct definition of the commodity and of the production set. So what's our definition of the BAD in question? It's CO2, but it's in fact net additions to atmospheric CO2, which we abbreviate NaACO, NaCO. So a kilogram of atmospheric CO2 is the same as any other one, regardless of when it was produced or how much electricity was generated. Different technologies for generating electricity can be taxed differently because we put the tax not on the electricity itself, but we put it on NACO. And that allows us to give incentives for greener generation technologies, and also potentially for offsets, although there's an active debate now about whether offsets like planting trees or use of biofuels are actually useful in this process. But in any case, we can, if we have a mitigation process that actually works, we can insert it into the pricing. And this is a more subtle point, I think, because it's not really an assumption formally in the model. The model just takes the production set as whatever it is. And I've criticized, I hope, convincingly, the assumption that there's free disposal in production. But in fact, just avoiding the assumption of free disposal in production doesn't really solve the problem. The production set Y must be exactly the set of technologically feasible input-output vectors. And all byproducts of production must be included so that they don't drop out of the accounting. Okay, if the production set Y includes things that are not technologically feasible, that means that stuff is dropping out of the accounting. And these are compatible with the formulation in Makarov. So aside from the unpleasant thing that the pollution all gets bought up in equilibrium typically by a very small group of poor people, Makarov is a solution to the problem. And the only thing we've added is some hopefully clearer thought about the assumptions. But the theorem about existence of equilibrium is in place and has been around for 40 years. We've just thought a little bit more clearly about how to relate that model to the situation we face. want to argue that consumption of NACO, I've put it in quotes, is really a production process. And this is related again to the issue of ownership in general equilibrium. I really want it to be the case that if I'm assigned a kilogram of NACO at equilibrium, I actually have voluntarily agreed to remove it from the atmosphere, and I actually go ahead and do that. Okay, and that's different from the way other commodities are treated in GE. So if I buy a painting or a piece of gold jewelry, I don't have to destroy it. I can display it and admire it. I can put it away in a vault, but I don't have to destroy it. And it's really critical that if I accept some NACO, that I actually do destroy it. I really have to get it out of the atmosphere. So the consumption of CO2 is really a production process. Okay, so here's where we get into the new mathematics. And we're going to look at the Erediver model with a measure space of agents. And the basic reason for this, well, there are two reasons. So the first is the four of us are mathematical economists. But the second is that we really need to do this as a way of trying to control this unpleasant feature of the finite models, that they stick a small group of people with responsibility for a large amount of the pollution, and that raises either equity considerations or suggests that they won't actually do it. They don't actually have the means to do it. So we want to get a model where we can think more clearly about how the assignment of goods to people affects whether it actually really does get held out of the atmosphere or not. It's also desirable to separate the competitive sector, so individual consumers who are individually negligible can affect prices, from firms, some of whom may need to be regulated because they're monopolies, because they have pricing power, because they emit pollution. So we're going to look at a model with a finite number of firms, but a measure space of agents. And there are three problems in doing that. The first is that the existing proof techniques, so this goes back to Alman almost 50 years ago, and follow-up literature, almost universally, they assume monotonic preferences. Okay. And the second is the failure of integrability. So a non-zero portion of the bads is consumed by a set of agents of measure zero. So this is the manifestation in the measure theoretic model of the problem I described earlier in the finite model, in which a very numerically small group of agents ends up consuming all of the CO2 or most of it. And it's either inequitable or infeasible for that to actually happen. What we actually see in the model is that in this setting of failure of integrability, the CO2 basically leaks away. So the set of measure zero is supposed to consume it, but it actually doesn't, and it gets released into the atmosphere anyway. And our non-free disposal equilibrium turns into a free disposal equilibrium. So this failure of integrability is intimately connected up with a leakage of the pollution into the atmosphere. We need to address that. And the third is a technical problem, which is not enough measurable sets that, typically in a measure theory model, you can describe the fundamentals of the model with respect to one measure theory, but the equilibrium then requires that you go to a measure space that has more measurable sets, that's richer. So this is something that's been well understood in probability, and it arises in mathematical economics as well. So the third resolution that works through mathematics in the measure theory models. So how do we do the existence proof, and how do we deal with the failure of integrability and relate that to free disposal? So non-standard analysis is a technique that allows you to construct an uncountable set that has all the formal properties of a finite set. And from that, you can derive a standard measure space called the Loeb space. So this literature in this first bullet dates back to the 1960s and 1970s in the mathematics and probability literature. And that's something that I worked a lot in, in the past, and it used certain techniques out of non-standard analysis. And then Kevin Duanmu, who's, as Lisa mentioned, one of the authors of this paper, but his PhD thesis in math at the University of Toronto 3 years ago, produced a real innovation within non-standard analysis, that it provided a general method to take theorems for finite mathematical systems and apply them to uncountable mathematical systems, including measure spaces. So what I would characterize this as, the construction he uses was known in the 1970s, but nobody realized that it was actually good for something. So I certainly knew about that. Peter Loeb, in a paper different from his more famous one that created the Loeb space, wrote about it. And nobody could figure out what it was good for. And Kevin's thesis shows that it's good for a bunch of stuff in probability theory and Markov processes. In particular, it allows you to take a theorem that's well known and known to be true and may actually be easy to prove in a finite system and extend it to a measure theory system. So we use Kevin's technique to extend Makarov's result, or result on existence of equilibrium in a finite economy, to measure space economies. And that lets us bypass the methodological problems of trying to adapt Almond's methods to cases where monotonicity of preferences fails. And I think quite interestingly, when we look through the proof, we can see a specific condition on the non-standard economy that's equivalent to the creation of additional free disposal. Okay, so we can find in our non-standard, it's called a hyperfinite economy. It's one of these economies with an uncountable set of agents, but it behaves like the one with a finite set. We've got a condition there, which is called S integrability. And S integrability fails if and only if the process of projecting back down into a measure space causes additional free disposal to be kind of hidden away or released. So we can see exactly where the leakage is coming from. Final resolution is the not enough measurable sets. And we do this in the paper in two ways. So the first is that we, looking at time here, and maybe I don't want to say too much about this one. In one sense, this is mathematically the most interesting and original part of the paper, and also probably the hardest to explain. So given the time is running a bit short, I think I'll pass on that. But this is where some of the most interesting mathematics occurs. So I'm going to describe our model. And for simplicity, I'm going to do it in the exchange case. And I have to say also, I probably should have said this right at the beginning, but my own view when I've taught the Erediver Model in first year PhD microeconomics, what I say to them is that general equilibrium is a very successful theorem in the exchange case, so very successful theory, So that if you take the production process as exogenous to the model, so it's happened, and then look at how individuals divvy up the commodities that result from that production, then general equilibrium is a very successful theory of that. And it's more problematic in the case of production. And for reasons, some of which we've seen in this talk and others that are true, going back, over the last 250 years, and that we don't resolve. I see Lisa's raised her hand, so Lisa? Or maybe she raised it a long time ago and I just noticed it, but Lisa, did you want to ask a question?
No, it completely accidental raise of hand.
Okay.
Touched the screen and as I should not have.
Okay, no problem. So anyway, so I like exchange economies much more than I like production economies because I think the theory works better and is closer to empirical reality. But in addition, it's a little bit simpler. And to simplify, I want to look at the measure theoretic model in just the exchange case. So we have probability space. So that's measure space where the measures of sets are all non-negative and the total measure is 1. Each agent's consumption set is, I've unfortunately changed my notation. That I should have changed capital K to little l, but let's go with the notation on the slide. We have an initial endowment map, which is a measurable function from the names of agents into their endowments, and it's integrable, and the initial endowment of the whole economy is strictly positive. So there's a positive amount of every good that's people want to consume. Okay, and the set of allocations is set of integrable mappings from T into the commodity space. And it can be equipped with either the L1 norm topology or the weak topology generated by L infinity. So this relates to the last slide. In order to get an equilibrium back in the measure theory model we started with, we want to assume its set of allocations is equipped with the weak topology. And this is going to affect the nature of externalities that we can allow. We also get a theorem in this stronger topology, which allows more general externalities. And P is the set of all continuous, transitive, aeroflexive, and convex preferences on the commodity space. We allow for negative prices. Okay, so we allow prices of some commodities, or even actually in theory, all commodities, to be negative. And the preference of agent T, we've got a function from the allocation. So my preference over my consumption depends on what everyone else is consuming. That's actually allowed to depend on the price as well. Okay, and it tells me what my preference is over my own consumption. Okay, but it depends on the allocation to all the agents and on the price. The budget set is then the set of all consumption vectors that you can afford by taking your endowment, selling it, and going and buying commodities. And given an allocation of goods to all agents, the demand set of agent T consists of all the things that maximize the preference over the budget set, where the preference depends on T. So P has two roles. It determines what the budget set is, and it also affects the preference, and the consumptions of every other agent also affect the preference of agent T. So if the electricity that someone somewhere is using was generated by releasing CO2 into the atmosphere, then I care about that. That affects my preferences, and if somebody next door is emitting particulate emission, then I care about that as well. And we get, just as in the finite case, either free disposal or non-free disposal equilibrium, and that's the total consumption has to be less than or equal to the total endowment in the case of free disposal equilibrium, or equal in the case of a non-free disposal equilibrium. So what goes into the proof that, so our theorem is that equilibrium exists in this model, and therefore, as a consequence of that, a computable general equilibrium model in this framework will actually also find an equilibrium in a computationally efficient way. Okay, so I can, if I make my model a little bit less abstract and put in some specific industries and perhaps countries, and then look at the effect of imposing various restrictions or modifications of price through a tax, I can actually make a prediction about who winners and losers are, and talk about whether I want to compensate them, and if so, how much. So that's the theorem we're trying to prove. And what do? Well, we use the technique that Kevin Duanmu developed to embed our probability space of agents in our model into a hyperfinite probability space. So again, this is a non-standard space that has all the formal first order properties of a finite probability space. We invoke an existence theorem for finite economies, either Makarov or we're also looking at alternatives, but Makarov will certainly do for our purposes, and we may be able to do better to find free disposal and non-free disposal equilibria of the hyperfinite economy. And this uses the assumption that preferences are convex. The Alman measure theoretic economies, you don't need to assume preferences are convex, but you do need, at least in the existing proof techniques, to assume monotonicity of preferences. And while we'd prefer not to assume preferences are convex, we're much happier to take that than to assume that preferences are monotonic. We convert the hyperfinite probability space to a standard measure space, the lobe space. So this is, so Kevin's technique is in the first two bullets. The third bullet uses non-standard analysis techniques from the 1970s. And then when preferences are weakly continuous, so this is a restriction on the externalities we allow, but it's certainly sufficient to allow for global warming through carbon dioxide emissions. We use convexity and conditional expectation to produce an equilibrium of the original economy. Okay, so we can show that there is an equilibrium in a measure theoretic economy which resolves the issues we described as being problematic for a model of global warming. Second part is, I think, also quite interesting. So as I noted earlier, first, in a finite economy model, a small group of agents, or even only one agent, can absorb most or all of the pollution. And in the lobe measure economy, that can happen for a set of agents of measure zero. Okay, a set of agents of measure zero may consume a non-negligible amount or even all of the pollution in the equilibrium. Okay, so here's what's going on there. In the hyperfinite equilibrium, this is the thing that's non-standard but looks like a finite economy logically. The projection of that is always an equilibrium in the lobe economy. But there's a specific condition in the hyperfinite economy, which is called S integrability. And if hyperfinite economy is a non-free disposal, so we've accounted for all the CO2, and S integrability holds, then the lobe equilibrium is also non-free disposal. And on the other hand, if the hyperfinite economy is not S integrable, then the lobe economy equilibrium always involves strictly more free disposal. So some stuff that was correctly accounted for in the hyperfinite economy gets left out of the accounting in the measure theoretic economy, and we can actually see what that is in the hyperfinite economy. And then we can also see exactly how it's happening in Hara's examples that are of this form. So here I'm getting into the mathematics, and I sort of skipped this earlier, and I think I'm going to skip it here only to say that the most original part of this mathematically and arguably also economically, although I'm not sure it's particularly relevant to global warming, is dealing what happens with the fact that there aren't enough measurable sets. And we have to end up defining our preferences over a larger collection of measurable allocations than they are in the original model. And we argue that we do that in a justifiable way. And we argue that this is a good solution of the original equilibrium existence problem, but we don't have a purely standard way to explain why it's a good solution. This is analogous to something that's well known in the theory of stochastic processes, that it's like the situation in which a stochastic differential equation that's stated on a particular measure space and filtration on that measure space doesn't have a solution. It only has a solution in a bigger space and bigger filtration. But it has a twist that isn't present in the case of stochastic differential equations. It's specific to the economics, and I don't think I can usefully say more about that. So let me turn to the conclusion and sum up what we've been trying to do and what we think we've done. So general equilibrium theory is almost 250 years old. In its developed form, it mostly goes back to the 1970s or early 1980s. But as of that development, it contains a number of aspects that are quite problematic when modeling climate change. And these were easily dismissed in a time when there was a lot of scarcity, and are not so easily dismissed now. And so we want to go back and rethink those. And we identify and we resolve those problematic aspects to a substantial degree. So many of these can be resolved in models with a finite set of agents. And there, the mathematics was developed by the early 1980s to do that. But what we've contributed is, we hope, clearer thinking about what the problems are and how you construct the model, and then invoke the results from the older literature to show that there is an equilibrium, and that equilibrium is computable. But part of the resolution also requires consideration of measure theoretic models. So that there's this awkward problem that in the finite models, the pollution ends up being consumed by a very small number of people who may not really be able to get rid of it. And the existing results for measure theoretic models require heavily on the problematic assumptions. And we use a non-standard analysis technique, which again is a new non-standard analysis technique. It's in terms of publication 3 years old, and in terms of development maybe 5 or 6 years old, and Kevin Dwanry's thesis, to provide a novel method for improving results for measure theoretic GE models by taking results for finite ones and kind of automatically extending them. And, we believe that this is a general technique that can be used elsewhere in economics and also has been used quite widely now in probability theory. And at this point, I'll stop, and if I haven't exhausted everyone, I'll be happy to take questions.
Thank you. Before I hand over to others' questions, I certainly have a lot, but I'll ask one. So you started with a very practical problem, which, as I understood it, motivated you to think about how standard economic equilibrium models work and how you might modify them to get something a little bit closer to the practical problem. And then there's this theoretical development, which from a distance looks quite beautiful. So my question is, can you bring it back to the practical problem? So now I'm the government and I want to make policy. How am I better able to do that given the theory you've provided us with?
Okay, so I think there are two answers to that. One is that you want to develop it's going to have to be simplified, as all macroeconomic models are simplified, but less abstract model of the economy that has specific industries in it, and apply the techniques of computable GE to them. So what our theorem tells us is that, yeah, there actually is an equilibrium, and computable GE methods will find it. So I would say, yes, you can go ahead and examine the impacts of cap and trade or carbon tax and use a computable GE model to see who the winners and losers are, and then make a decision about whether particular losers deserve compensation and how much to give. In order to decide how much to compensate them, you need to estimate how much they're going to lose. So I think that's the practical implication of it.
Thank you for that. Okay, audience, anyone got a question?
Hey Bob, I have a question. So
Yeah.
here, why do you need the continuous model instead of finite, just like finite agent?
Well, because the equilibrium in the finite agent model, so I haven't shown you the specific examples, but they tend to have this property of all of the CO2 is being absorbed by a small number of people, and we don't believe that. I mean, we don't believe it's feasible for them to do that, and so we want to have some discipline over it. Now, an alternative might be to simply build that into your finite model in a different way, and if so, you wouldn't need the measure theory model. But this is a way to impose some discipline to prevent that from happening, and also to see exactly where the leakage occurs. So where stuff that you think is being absorbed actually is leaking and gets disposed of. So I guess that's the answer. An alternative which perhaps could work in the finite model is to just control better what people are allowed to buy. So it simply prevent people from who say they'll take a large amount of CO2 and dispose of it, and simply then renege on that commitment.
I see. Yeah. So another question is is that possible to incorporate some historical data, for example, in terms of fairness? Some developing countries, they have different history or the CO2 like the
Yeah.
consumption or all this stuff, and so the how to say quantify the prices
Yep.
by
So
incorporating the history into the GE framework.
So I think there are two equity issues that have not really been addressed in the framework. So I don't think this has much to do with our model, but it's important in terms of policy for global warming. So the Paris Agreement and the Kyoto Protocol before it both set goals in terms of reduction of emissions from historic levels. And of course, that basing on historic levels gives a big advantage to developed countries that are currently, or in the recent past, have been emitting a lot. I think that that's really impossible to justify from an ethical or equity standpoint. A much more reasonable thing would be to give every individual on Earth a certain entitlement to emit, and then require industries or individuals or countries that want to emit more to buy it from those individuals. And it would also have the beneficial effects. So this is part of the good aspect of general equilibrium, the Pareto optimality. It would mean that the incentives to avoid emissions would be the same in poor countries and in big countries, and it would involve an automatic degree of compensation for losers in the less developed countries. So that's something that I believe in, and I said I think it's not largely connected with this, but it may be in terms of the applicability of the first welfare theorem. Now, the other issue is whether countries that historically emitted should be penalized for doing that. So right now, in some sense, they're advantaged. What I suggested, everybody gets a certain right to emit, would put everybody on an equal footing, but maybe you should penalize countries that have historically emitted a lot of this. And that, is a very complex philosophical issue, because are the people who currently live there responsible for what earlier generations in those countries did? It's like the issue about reparations for slavery, for example. It's something that I think is not really in the framework of economics, and it's much more to do with ethics and philosophy. But I think both issues are real, and neither of them is addressed in the Paris Agreement or the Kyoto Protocol.
Yeah, thank you for the insights.
Any further questions?
Yeah, I have one. What happens in these models when there's lots of uncertainty on what you're measuring, or is that outside the scope?
Well, it potentially is within the scope. So the Erediver Model can incorporate uncertainty, and you simply describe various states of the world, and instead of trading commodities, you trade contingent claims for those commodities. So in principle, it could be incorporated. We haven't really thought about doing that in a practical way, but I guess in principle it's there, and if we thought some more about it, then we could probably talk more sensibly. But right now, I don't know. We haven't really thought about it hard.
Yeah, I've seen problems arise in other models when you assume parameter uncertainty. But one thing you may be aware of, in the remote sensing world, there's this discussion of using sensors to track CO2 emission and then put that in a distributed ledger. So that that could be one way to at least eliminate that problem, the actual measurement, which continues to be an issue.
Yeah, and there's a complex problems about where you want to impose the tax. So, so do you certainly want to tax the electricity generator in order to give the right incentives between using coal and, let's say, using solar. So you need a tax there, but you also need to give incentives to consumers to turn off their lights or put in LED bulbs rather than incandescents. And exactly where you want to levy those taxes is, I think, a complex question as well. And I guess the way you would resolve it in these models is to figure out in detail what the commodities are. So I focus on saying we want NACO, atmospheric emissions, to be a commodity, but maybe you want to more carefully delineate other commodities as well, in order to give as many people as possible the right incentives.
Great.
Yeah, I agree.
So we're a little bit over, so I think that's all the time we're going to have for questions today. If there are further questions, please write into the seminar organizer, Regine, and we can get, or to write to Bob directly, and we can get them answered. Let's thank Bob for a really beautiful talk. I'll just clap here. And mention that next week at the regular time, we have Alexander Braun, who will be coming to us from the University of St. Gallen, that's in Switzerland near Zurich, and is also talking about the topic of climate and economics. He's discussing a more local problem coming out of the global problem Bob mentioned, which is hurricane exposure in the US. Many of us, I think, believe that CO2 has something to do with that. So I hope to see many of you next week at our regular time, and wish you a great rest of day.